In this problem, we need to design a fence. We're trying to fence in 1,000 square foot area, and it's in the shape of a rectangle. So the result will look like this, with 1,000 square feet inside. And the costs of the various sides of the fencing are different. There are 3 sides that cost $3 per foot. That's this side, and this, the top, and the far side, we'll say. And there's one side that costs $12 per foot. Alright. Now in the beginning, I'm just arbitrarily assigning these to the various sides because it's a rectangle. One of the 4 sides is going to be the expensive side per foot, and the other 3 are going to be the cheaper rate. The way I've drawn this, it looks like the long side will be most expensive, but I don't necessarily know that's how it's going to come out. But as you read through the rest of the problem, you realize this is an optimization problem. We're asked to find the dimensions, so I've got to give the length and width that will minimize the total cost of this project. And there's keywords here that I always look for. So I'm either trying to find a maximum or minimum in these. In this case, it's a minimum. And I want to know what is it that I'm trying to minimize. And in this case, it's the total cost. And this is real key for me because this tells me what sort of function I need to build and analyze. I need to build a function that describes for me the total cost of this project and then find the minimum value of that function. Alright, so I'm going to let my function be C for cost, and I need it as a function of only one variable. Which variable is up to me. I can pick whatever letter I like from the alphabet. But this variable that I select will give me the various layouts of my rectangle. So I'm going to go over here and label my drawing. And there's more than one way to go about this as well, but I'm going to let X be the length of the expensive side. Alright, so I'm going to let X equal the length in feet, same as the other 2 sides. This is a rectangle, not a square. So we can label this with some other value, say Y. Alright, and then what we need to do is try and figure out a relationship between X and Y. If I want this to be a function of a single variable, say X, then what I write here can have only X's in it. Alright, in our drawing, we're letting Y equal the length in feet of the left and right sides in our drawing. Alright, and again, the total cost of this project, we could just walk around and add up the costs of all of these various sides. This side here is going to be $12 per foot with X feet of fence. So the cost on this side is going to be 12 times X. There's going to be a 12X in here for that. The cost of the far side is $3 per foot and its length X, so it'll be 3X. The other 2 sides, however, are now going to involve Y, which our function here needs to be a function of X, but I'm going to go ahead and write the Y's in there, realizing that the Y values actually depend on X, and later on I'll come back in and replace them by the appropriate expression in X. So this side here is Y feet long and $3 a foot, so its cost will be 3Y, and the far side, same thing, 3Y. Now the question I've got to answer before I move much further is, what is the relationship between X and Y? How can I rewrite Y as a function of X so that I end up with a function of only one variable here? And the key here is this other piece of information I was given. If I know the length on one side, I really do know the length on the other side, because I've got to have the product end up being 1,000. So for example, if this side was 10, then in order to get 100 square feet inside, this side would have to be 100. And if you just write that down, we need, well, note this, X times Y equals 1,000. then y must be 1,000 over x. I just used a little algebra to solve for y. So our cost function here is going to be 12x's plus 3x's plus 3y's, which we'll write as 1,000 over x, plus 3 more. And that's the function that I need to analyze. And on these types of problems, setting up the mathematical model is perhaps the most challenging part of this. From here on out, it becomes at least more familiar. Let's just put it that way. Let's simplify this down a little bit. 12x and 3x is 15x. I've got 3,000 over x plus 3,000 over x would be 6,000 over x. And now I'm ready to begin the calculus portion of this, which is to find the minimum of this function. And I start to think about how I'm going to justify that I've found the minimum before I even go searching for it. There are basically 3 or 4 basic techniques here. If this were a parabola, I would go after the vertex. That would give me a lot of information. But this is not a parabola, so that's simply not going to work. If this was a continuous function on a closed interval, I could use the extreme value theorem. But I don't have an upper bound on x. I don't know what goes up here. And the lower bound is 0. I can't have a negative length on my side, but I can't actually let it be 0. This function's domain does not allow for that. So this is not a closed domain. It's open on the left and open-ended on the right as well. So extreme value theorem's not going to work for me. I can't make a statement like, well, x has to be at least 1 and at most 1,000, something like that. That just doesn't fit. So about the only way to approach this is the sign distribution for the first derivative. So I'm going to draw out a sign distribution for my first derivative. And for that, I will need the first derivative. I know at 0 I'll get a does not exist here already because the function doesn't exist there, and I don't care what's going on to the left. I'm only interested in what's going on the right side. The derivative of 15x is 15. The derivative of the 6,000 over x, if I rewrite this x as an x to the minus 1 up here, then the derivative would be minus 6,000 x to the minus 2. And x to the minus 2 I can rewrite then as an x squared in the denominator. Right? Now I need to know values where this derivative is 0 and where it does not exist. The d/e at 0 is now obvious, but where does it equal 0 is my latest question. This is my critical value. And if I do some algebra, let's move this 6,000 over x squared to the other side. I get that 15's got to be 6,000 over x squared, or x squared has to be 6,000 over 15, which is the number, let's see, that works out to be 400. All right, and so x is going to be plus or minus the square root. X is going to be equal to plus or minus the square root of 400, which is 20. And of course, the positive square root's the only one that fits in here. So there will be a derivative derivative value of 0 at x equal 20. And we can now check our signs. If x is much larger than 20, then I'll be subtracting less here in my derivative. So this will certainly be positive, which means the costs are increasing out here. If x is smaller than 20 but larger than 0, then I will be, let's just pick an x value, say 1. That's an easy one. This would be 15 minus